Okay, so welcome everyone. This is the tutorial on speeding up R code. If that wasn't what you're expecting, you're probably in the wrong room. Either that or I am. Bit of introduction. I'm a biostatistician. I've been using R since 1996, which is longer than most of you, looking at Luke lurking in the back there. It's so a range of things, simulations, analyzing air pollution time series, big genetic data, genome-wide association studies, big surveys. And so across a reasonably wide range of things that might be too slow. I also wrote the R memory profiler, which is my only sort of contribution to actual speeding things up, at least the first version of it. This is a tutorial. You should ask questions. The questions Weka wants you to ask questions, and we'll come after you if you don't. So let's find out a bit about who's here. So let's see. So everybody here, I'm fairly sure everyone here uses R. We tried that in the last tutorial and got pretty good. Okay, so at people at universities, hands up. Yes. People, let's see, people who also use Python? Yep. Also use a C-like language? So quite a lot of sort of programming things. People who also use Lisp. Let's see. We had universities, big companies, big-ish companies, government, quite a few. Okay. Yep. Data, big data. People who use big data. People who use things your manager thinks is big data? Yep, okay, good. So it's a reasonable, or in the equivalent in a university, things your supervisor thinks is big data. Yep. Okay, so it gives a reasonable idea of the sort of audience. Okay, so R. R is slow. There was something that I used to have in the start of R courses saying that R is well known to be slow and unable to handle large data sets, which is true, except that computers are fast and computer memory is large, so it's very rarely a problem. But sometimes it is a problem. And R is slow for a bunch of reasons. One is that it's flexible. Everything can be redefined all the time. Despite Luke has been making valiant efforts to cut down some of this, but everything can be redefined dynamically all the time, and so that means that R has to look up what the current meaning of pi or the multiplication symbol or whatever is every time it wants to use it. It passes arguments by value. So if you pass a great big DNA sequence to a function, that function semantically gets a copy of the great big DNA sequence. R can sometimes avoid making those copies, but less often than you'd think. R is also slow because the bottlenecks in computation have changed since the early 1990s. So for example, R doesn't have a single precision floating point data type, because in the 1990s these weren't useful. The floating point coprocessors could do double precision just as fast as single precision, and there just wasn't a point. Now they're enormously useful because getting stuff on and off the chip is the big bottleneck in all computing, and so the bottlenecks have changed since R was first designed. And also, as you may have noticed, there are quite a lot of people who use R. And that means you can't break it. So R core, if you had huge resources, you could break it and fix it and catch up in time. But basically, the R community doesn't have the resources to break lots of things. We can't break things very often, and we can't break very many things. And so that, again, means that it's hard to do really major optimizations. So as a result, R is very slow. So we're going to look at ways of speeding up R code. The most important part of this is timing and profiling. Then look a bit at memory allocation, types of storage that are faster or slower, particular functions that you might not have realized were slow, the vectorization, which I'm sure you've heard of, and the sort of time and memory trade-offs you get when problems get bigger that way, and using some other tools, parallel computing, databases, other on-disk data representations, sparse matrices, things that for particular problems can get you huge improvements in speed. And then as a sort of epilogue, this is after all statistics, and so I'll talk a little bit about some situations where randomized algorithms can get you huge speed improvements, again in special cases, but special cases relevant to quite a lot of statistics. So some quotes from the canon. The famous one, of course, is Donald Knuth. That premature optimization is the root of all evil. Here's the longer version of that. We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. Yet we should not pass up our opportunities in that critical 3%. Life is short, the craft long, opportunity fleeting, experiment perilous, judgment difficult. Hippocrates was talking about medicine. Fortunately, one difference here is that experiment isn't perilous. You can quite easily do experiments to see what, you often can't guess what types of changes to your code will speed it up, but you can do experiments. And then a very important one from Brian Ripley some time ago, R has changed quite a lot recently, and older preconceptions do need to be checked against current information. R does keep changing, and so these slides were written, I'm still running R 3.4 point something on my laptop because that's what we have on our teaching image in Auckland. If you're running on R 3.5, then you'll find that the relative timings of things are different. Things change. So strategies, if you've got code, you start off with code. When you first write your code, it doesn't work and it's slow. And you have the choice of trying to debug it first or trying to optimize it first. This is not what the mathematicians would call a commutative diagram. There is one path that works and one that doesn't. So you want to debug it first so you've got correct code and then optimize it. Partly because debugging optimized code is harder, and partly because if you make it correct first, you'll at least have code that produces the right answers, and you can see when you optimize it and it breaks, you'll be able to see exactly where it starts giving different answers. And yes, in a sense, this is obvious, but on the other hand, it's quite hard to remember to keep doing it. And then, so this is the sort of strategy. This is a very recent xkcd cartoon. I should have done a hands up, who knows about xkcd, but I'm sure it's pretty much everyone. How long can you work on making a routine task more efficient before you're spending more time than you save? And if you're something that you do daily, in the middle here, and that you can shave a minute off, it's worth spending a day doing that. It will pay back over 5 years. If you do it less often than daily, or you can save less than a minute off it, then it's not worth it. It's easy to spend, optimization can be fun, and it's easy to spend a lot of effort getting the extra few % performance out of your code. But unless your code is run a lot, you shouldn't do that. If it's run a lot by you, or if it's run by lots and lots of people occasionally, then it's worth it. And so, for example, a lot of effort has gone into speeding up R's startup because lots of people start up R quite often. And so the sort of cumulative burden of time of an extra second in R startup is actually worth going after. But if it's a package that only you use, the extra second is just not worth the effort, unless you're doing it just for fun, which is, okay, fine. Okay, so let's get to some actual stuff. Timing and profiling. You need to measure your code to find out what needs to be optimized, if anything. Because if you can't reliably guess which bits of your code are slow, or at least I can't. And so measuring is the only way. If you measure which bits of your code are slow, you can at least optimize where it's got some chance of mattering. Or alternatively, you can find that your code is spending all of its time in R norm, in which case you don't have much hope of optimizing it. You may as well give up or find a different algorithm or something. So tools, we've got rprof, the sampling profiler, rproffmem, the memory profiler, tracemem, which another memory thing, and then profviz is a tool for looking at profile output, and microbenchmark is another timing thing. There's some complication in recent versions of R. In particularly, I think the R3.4 versions, code gets faster as you run it. There's a just-in-time compiler so that when you load code first, it's relatively slow, and then it gets compiled and it speeds up as you run it. And so you need to either turn off the just-in-time compiler if you want to know what the sort of first pass speed is, or run your code a few times before you time it. In version 3.5, packages are compiled at install time. I don't think source compiles. Does anyone happen to know? Source doesn't compile so code that you just load with source, it's still like this, that it's compiled when it runs, but packages are compiled at install time by default. So we've still got this issue in 3.5 if you've got your own code, your timing. So what are the tools? The most important one is rprof, which is a time sampling profiler. So every so often, the default is 50 times a second, it writes a stack trace to disk. So it looks the same sort of thing that traceback gives you. What function is currently running, what was that called from, what was that called from, what was that called from, all the way up. And so that's written out to disk, and you can look at it later. And optionally, it also writes out the current memory usage and the number of times that vectors have been duplicated with a call to duplicate internally since the last time tick. So that it's only sampling, it's only statistical, but again, we're statisticians, we know that, that sampling actually works, and if you've got a sample, unless you've got some particularly regular periodic thing in your code, if you sample it 50 times a second, you'll get pretty good coverage after a while of how much time your code spends in each particular, how much time the computer spends in each particular piece of your code. And profviz is a package for displaying rprof output. There has nearly been a better package, one that shows you actually call graph information, for a long time. There still nearly is. And we have hopes on for its actual appearance in the future. So that's rprof. rproffmem is a memory allocation profiler. So it writes out information to disk every time memory is allocated. So there's two parts to that. First, so internally in R, there's two sorts of memory allocations. Small objects get allocated on the internal R heap, And large objects get allocated by the operating system, where large means bigger than 128 bytes. It's small values of large. And so our proofman writes out information to disk every time a large object is allocated and every time a new heap page is allocated. So that's useful for tracking where your memory allocation is happening. In particular, it's useful if you want to track memory allocations of a particular size, because there's a lot of memory being allocated all the time and it's messy and it's just you don't want to go there. But for example, if you know that a column of your data set is exactly 43,226 bytes, then you can look for allocations of that size and that will tell you about copying of columns of your data set, that sort of thing. Often, when you're working with reasonably large data, you have a single large object and as few copies of it as possible. And one of the optimization goals is to get that down to, one, preferably, perhaps two. And so that's what tracemem is designed for. So you trace a particular object, and every time R duplicates that object, you get a message printed on the screen. And so it's only going to be useful if that's a fairly rare occurrence. If it's being duplicated 50 times a second, your screen will just fill up. But if you're trying to get it down from 10 duplications to 3 or something, then it's quite a useful tool. It was put into for the early days of genomics data in R, when people were having things like a gene expression, gene chip data set. And so the people in the bioconductor project were trying to say, we've got this object, what are all the places it gets copied in R so we can try and get rid of a few of them. And then microbenchmark is high resolution, high precision timing for small bits of code. So what it does is it runs your piece of code a lot of times and gives you the statistics of how long it ran. And so you get a better, you get a more accurate and stable idea of how long it's going to take than if you just ran it once. This isn't really useful for running your whole calculation, since if you're trying to optimize your whole calculation, then it must take long enough that you don't want to run it 100 times just for measurement purposes. But it's useful for optimizing for looking at little code fragments, and also for getting experience about what sorts of changes can matter. Most of these are also discussed in quite nicely in Hadley Wickham's Advanced R. The exception is tracemem, which he mentions but doesn't use because its output is printed on the screen rather than returned, and that's a pain if you're trying to write a book in Bookdown or whatever. So, okay, so one that you've probably seen before. Here we've got an object that we're going to keep making bigger. So we start off with a 0-length vector, and we go around a loop 100,000 times. Each time we add something extra to the end of the vector. And it takes 20 seconds. Also, in particular, it takes a lot of system time. That's often an indication that you're doing a lot of memory allocation, so that you're spending a lot of time allocating and recycling memory. And 100,000 isn't very big nowadays. 100,000 integers is 400,000 bytes, so it's half a megabyte plus a little bit of annotation. So it's not a lot of memory. The problem is that it has to be reallocated basically every time around the loop. So you allocate something of length 57, then you put something on the end of it and it's now of length 58 and it doesn't fit and it needs to be moved somewhere else, potentially. Now nobody would relatively few people would actually write this code, but you do get the same sort of thing happening with less trivial examples as I'll show soon. But if we look at the dumb example, so that's taking 25 seconds. If we pre-allocate the space, let's say we're going to have a vector of length 100,000, and then we just stick in the first element, the second element, and so on all the way along. That's taking about a 20th of a second, so it's about 400 times faster. And that's a good 400 times as a sort of, that's the sort of order of magnitude of difference between interpreted R and compiled C, sort of 400 to 1,000 times. So you're doing pretty well if you can get that sort of speed improvement in something. In this case, we can do even better because it's actually a stupid piece of code to have a loop in. We can vectorize it. We can just take that vector and square them all. And it takes then, we can see micro benchmark working here. It takes on average, well, the median is about half a millisecond. So that's 100 times faster than the pre-allocated code. So that's a sort of extreme example of what you can do with, if you're very lucky with optimization. We got a 20-fold, we got a 400-fold improvement, and then another 100-fold on top of that. You need to start off with fairly bad code to get that sort of improvement. Now, that, as I said, people wouldn't typically write that sort of code, but you end up often trying to write code that's sort of morally equivalent to that if you don't know how long the object is eventually going to be. It's easy, if you know how long it's going to be, you just allocate that much space and fill in the data. But if you don't know how long it's going to be, it's a bit more difficult. So, not so long ago, I did actually write code rather like that. I was interested in computing accurate p-values in the extreme right tail of a quadratic form in Gaussians. These come up in some DNA association tests. And there's an algorithm for doing this that uses symbolic algebra on a basis of gamma functions. And so the main point about that is that you have, each time you add an extra term, you've got this set of coefficients, coefficient and then which element of the basis it is, and every time you do an operation it turns into a bigger list, and it's not easy to predict in advance how much bigger. So the old code, which had 90% of its time in the C function, we had two things we were combining. So we had loops over their lengths. We have, which I'm not showing you, the code that actually does the complicated symbolic algebra stuff. And then that returned a variable length list of new coefficients. And so what I did was to use C to concatenate them onto the existing bits of code. And there, it's not trivial to pre-allocate this because you don't know how big those things are going to be. In order to find out how big they're going to be, you actually have to do the computation. There isn't a shortcut. However, you can get an upper bound on how big they're going to be. And so in this code, we say that, what are we doing here? Oh yes, so we say that we've made a set of vectors that are big enough to hold the upper bound on how long the vector is going to be. So the number of terms you get is hard to predict, but it's no more than the product of the number of terms in the two things you're putting in. I think that's the bound. There's some bound like that that's fairly straightforward but very loose. And so each time round the loop, we look at how many did we get back, we slot them into the results vector, and we have this cursor here that says how far we've gone along the vector. So we're slotting in, we get 10 terms, they go in the next 10 slots in the vector. Or you could keep them all as a whole lot of little vectors, and then at the end put them together with one call to C using do.call. That gives you simpler code. I think this gives you faster code. And as usual, there are trade-offs. That the fast code isn't usually, the fastest code isn't usually the most straightforward. But so this is an example of the pre-allocation problem coming up in real code by somebody who does more or less know what they're doing, and fixing it gave a 10-fold speed improvement. So it's worth writing code like this to get it written faster, to get the code written and checked and debugged and working. But then it's also worth writing code like this to get the 10-fold speed improvement. So that's the basic principle there is well known. It's just that, you know, it really does occur. It's not just something it's not just a straw man. Memory copying, there's the R pass by value illusion, that R behaves as if functions get copies of their arguments, and they're not copied unless they're modified. So if the function doesn't modify the arguments it's passed, they're not copied. If they are modified, then occasionally they're not copied, if R can prove that it doesn't need to. And basically this is primitive operations on local variables that have never been passed to a function. But the impact can be quite dramatic. Here we've got a piece of pointless code that squares the elements of the very long vector. We've got two very long vectors. And we have this function touch, which just, its purpose is to confuse R about whether it's safe to modify that vector. So all it does is all this function does is pass x to a function. If we do this, then R doesn't know that x is safe to modify in place, and the code takes 45 seconds. If the thing we touch is y instead of x, then R does know that x is safe to modify, and we take 0.2 of a second. So there's a really dramatic speed difference here. This is something that it's relatively unusual you can take advantage of, but sometimes you can, and it's a huge difference. So there's the special case here is if you're only doing primitive operations like subsetting a vector on local variables, and so those are reasonably controllable, and local variables that have never been passed to a function, because once a variable's been sort of potentially contaminated, it can never be restored again. R has a very simple counter of how many references there are to a variable, and it goes sort of 0, 1, many. And that's why you end up with this sort of strange behavior. If you had something that counted the actual number of references, then you could go, it would increase and then decrease and so on. You could see if it was currently just 1. But we don't have that system. We have a 0, 1, many counting system. So that's, in a sense, that's an example of why relatively small changes to code can produce quite dramatic speed differences, and you have to try changes and see. A more sort of realistic or more sort of more commonly used issue, data frames are quite slow. That's partly because they do some quite complicated things, and partly because a lot of the code's still interpreted, because it would be a real pain to write actually compatible compiled code. Here we've got a data frame from the American Community Survey, 152,000 records, 300 variables. If we want to sum the values in one of the columns, then we're taking about 10 microseconds. If we had the same thing as a list and wanted to sum the values in one of the columns, we're taking about half a microsecond. So it's about a 20-fold overhead there using a data frame instead of using a list. Now, lists are much less useful than data frames. You don't get all the nice two-dimensional indexing on them. And sometimes, so you'd obviously want to start off with data frames, but if you need the extra speed, then going to lists or matrices can make a big difference. So here's the matrix version of, let's see, yes, so here's the matrix version. Here we've got a matrix, numeric 5,000 by 4,000. We can take the column means of that matrix in about a 40th of a second. But if we turn it into a data frame, taking the column means of the data frame takes about 10 times as long. So data frames have a lot of extra information and structure in them that lists and matrices don't, but there's a fairly substantial computational penalty for that, particularly when you have a lot of, for big ones, either a lot of rows or a lot of columns or both. And here, taking a little rectangle out of the middle of a matrix, that's taking about 10 microseconds. Taking it out of the middle of the data frame is a lot slower. So data frames are things, you know, you obviously want to use a structure like that most of the time, but if you've got code that's time critical and you can get away with a list or a matrix, then that will be potentially a lot faster. There are, of course, other alternatives to data frames. There are tables and there's the data.table package. And they're both faster than the base data frames. They both claim they're compatible. This isn't true. Neither of them is actually compatible. But they're not very different. And if you have to rewrite your code anyway, a useful step is to maybe to rewrite it as a data table first and see if that's good enough. But if you do need to then check whether the things you're working with are data frames, because the other annoying thing about both these things is that is.data.frame returns true for both these classes of things, even though they're not data frames. This is annoying when you're writing code and trying to test what sort of objects you've been passed.
So you would always recommend if you would have really large sets of data, maybe 100 billion rows and 20 columns or such, you would always recommend to do any kinds of calculations in matrices?
Yes, though if it was 100, in that situation I might also recommend not having it all in memory at once. It depends on what you wanted to do with it. And so I might well recommend not even having it in memory. So having it in, so it depends on what sorts of calculations you're doing to it, but some big data sets you'd be better off having them in a database and doing, if you're doing simple calculations to them, or if you're doing calculations on subsets of them, having them in some sort of fast access format on disk so you can read in chunks rapidly. Because it depends on how big, I mean 100 million by 20, that's 22 billion. So that's getting to be quite a lot of memory. That's on the order of 16 gigabytes of memory for the thing itself. And so if you don't have 3 times, sort of rule of thumb is that R starts to slow down when objects are more than about a third the size of physical memory. So if you only had 32 or 16 gigabytes of memory, you'd want to avoid having that object in memory at all, the whole object, yeah. But if you did have it in memory, then a matrix would be a lot better than a data frame. I haven't. I've used netcdf. I've used instead of HDF5 is more flexible, but at the time when we were doing genome-wide association studies, and also before that flow cytometry things, that HDF5 R interface wasn't very stable at that time. And so we used netcdf, which was nice and easy. But HDF5 seems to be a lot better, potentially. I just haven't used it. Because that was the original, back in the early days of Bioconductor, when Robert Gentleman was looking at this sort of problem, HDF4, as it was then, was what they were going to use. But memory, PC memories grew fast enough that you didn't need to do that for gene expression data. And so they stopped. But that was the idea back then.
Okay. Thank you.
More questions? Yep.
If data.frame returns true, how do you actually tell it?
Well, if you know, so for say Tibble, there's an is.tibble function which you can use, and at one point for internal use in one of my packages, I wrote an is.honestly.data.frame, where so basically if it's data frame and no other classes, then it's really a data frame. The problem there is you could have something that inherits compatibly from data frame, and there's no way of telling that in general. You just need to know that the likely things are data.table and tibbles and watch out for them. I mean, I get I have on multiple occasions got bug reports for the survey package that are due to people where, the place that's documented to take a data frame, it's had a tibble or a data table passed in, and they don't do exactly the same things. So now the code checks, but initially it didn't. Encoding, so plain text. As I hope everybody knows by now, except possibly some Americans who can get away with not knowing, there's no such thing as plain text. That there are, in order to get, you have sequences of bytes. In order to tell what text is represented by a sequence of bytes, you need to know the encoding. And in the old days, the encoding was ASCII, and you got the American alphabet out of it. And then, things progressed a bit, and you could get things like the Latin 1 code page, and you could get the Western European alphabets, or you could get the New Zealand code page, and you could be able to put New Zealand place names in. Or there's UTF-8, which can represent everything from English to Klingon, but uses variable numbers of bytes per letter. So you could have UTF-8, which is what R is mostly tries to use. And so that's a variable length encoding. Some characters use 1 byte, some use 2, some use 3, some use 4. You could have Latin 1, which is a 1 byte per character thing that works for Western European languages. You could have your local encoding. If you're in New Zealand, it will let you do Maori place names. If you're in China, it's just complicated. It's even more complicated if you're in Vietnam, where it is a 1 byte per character thing, but it's really, really packed tightly into the 1 byte. Or you could have just plain bytes. You could have a string of bytes, and you could just be thinking of them as bytes and not particularly as text. UTF-8 is preferable in lots of ways, but the variable character lengths make some operations on it relatively slow. This used to be a much more serious problem than it is now. It used to be that the regular expression parsers on UTF-8 were just terrible, and now they've been optimized a lot over the years. But here we have an example of a long string, which I think is 10 to the 5 copies of that one word, facile. And we have, this is a string that you can represent in Latin 1. You can also represent it in UTF-8. Or you can just have the set of bytes considered as a set of bytes. And so that's what these three are. They're the same string, but the first one is in Latin 1, the second one is in UTF-8, and the third is just in bytes. And you can see the first two print exactly the same. The third one has got this unprintable byte that occurs once per word. For the C was a cedilla. So if we look at finding a string in there, this is a string that isn't in there. It takes about the same amount of time. Well, no, sorry. Which way round are they? Yes. So Latin 1, so UTF-8 and Latin 1 are sort of comparable, though the worst cases are a bit different. And the plain bytes is a lot faster. It's about three times as fast. And that's not surprising that it's not surprising that the UTF-8 is slower, because you have to keep finding where you are. It's a bit surprising that the Latin 1 is slower. I'm not sure why that's happening. Or if you want to take a substring, so here we're taking a substring from the middle of the string, and to do this in UTF-8 you need to find where the 1000th character is, and there's no way to do that except by starting at the beginning and counting, because you don't know how many bytes per character it's going to take. So as a result, UTF-8 is quite a bit slower than either of the others in extracting this substring. And this is in a situation where there actually isn't a whole lot of variation in character length. If you were doing something in a mixture of languages, it could be a lot worse. So encodings, and again, you don't usually want to mess around with encodings if you can avoid it, but sometimes if you're in situations where speed really matters, then the encoding can matter, and it may be worth using a less flexible encoding than UTF-8. Okay. I mentioned matrices being faster than data frames. There are also things you can do to speed up matrices. The mechanism for this, there is a thing called the basic linear algebra subsystem, which defines all the basic matrix and vector operations that you need for linear algebra. And they're defined in a nice standardized form so that anyone can write their own implementation of BLAS and just plug it in instead of the existing one. Now, the matrix operations in R are already in C. It's not that the code has obvious inefficiencies of the sort that you're used to in R. It's that the speed of linear algebra, in the old days, the speed of linear algebra was about the speed of floating point computations, that if you want to invert a matrix, an n by n matrix, you need to do n cubed floating point operations, and that was the bottleneck. Nowadays it's not the bottleneck. The bottleneck is getting the matrix on and off the chip. And using an and so the versions of BLAS that you can get that some compiler vendors provide, and there's also some open source ones, they optimize in two ways. They optimize getting the data on and off the chip, and they also optimize, in some cases, the use of instructions that can operate on more than one number at a time, the sort of vector processing instructions on modern CPUs. It's surprising. It's one of these things that, when I learnt computer science, the idea, the sort of model of computational complexity was that there was memory, and access to memory was basically free, and then there were operations that you did on the things you got in and out of memory, and you counted how many of them there were, and that's how you worked out how long whether one algorithm was faster or slower than another. But you can do an enormous amount of work in the time it takes to get a number all the way from memory onto the CPU. And nowadays, the big effort of a CPU is moving data around, and actually computing on it's a sort of bit secondary. The basic principle is so one important principle is you don't write your own linear algebra, you let the professionals do it. And the other one is that you can get substitute versions of the basic linear algebra subsystem and plug them into R very easily, and it can make a difference. So here we've got a medium-sized matrix, 1,000 by 2,000 matrix. We take the cross product of it to get 1,000 by 1,000 square matrix, and then invert that square matrix. So this is using the BLAS that comes with R, the standard reference BLAS, and this is using the Apple Veclib one that Apple supplies. And you can see there's an order of magnitude speed difference. Part of that is threading, but a lot of it is optimizing cache and complicated stuff that I don't understand. There are other, there's something called OpenBLAS, which is a portable one for, relatively portable one for Intel chips. There's all sorts of things that can be optimized about BLAS, and they include sort of excruciatingly boring things like the translation look-aside buffer, which is the thing that translates the memory addresses your program thinks it has to the actual physical memory addresses on the chip. And people who care about this sort of thing have put an enormous amount of effort into optimizing these, and it makes a difference. So you do get slightly less good accuracy with some of these. So if you actually need last digit accuracy, then you may need the reference BLAS, since it's sort of by definition, it's accurate in the sense that it defines what the right answer is. But some of these other ones you can lose a few digits accuracy here and there. But since we've got 15 digits accuracy to work with, that's actually fine for most of us most of the time. So that's something where a lot of people might not have realized was even a potential for improving speed. And this is another example of the same sort of thing that people wouldn't have considered was a problem. So two sorts of commonly used functions that are enormously less efficient than you probably think they are. So the if-else function, which does vectorized operations, conditional operations, and Pmax and Pmin that do this for minimum and maximum. The reason these are slow is that they put a lot of work into doing the right thing. So firstly, the question is, what's the return type of these? And it actually depends, for if-else, it actually depends on whether the conditionals are all true, so if-else only evaluates both its arguments if it has to. And so if it's all true, it doesn't evaluate the false argument. If they're all false, it doesn't evaluate the true argument. And that means that the return type could be different, and it's just all complicated. You might just say that it shouldn't be complicated like that, and you would have a reasonable case, but it is. And as a result, if you want to do, instead of that, you can try that, and it will often be faster. Let's see if we have an example. We do have an example. Okay. I think this is one we're actually running. So comparing these two, the if-else versus the subscripting approach, we're getting a mean of about 80 microseconds versus about 30 microseconds, which I keep forgetting that Ifelse can make such a big difference and being surprised and then coming back to it. Here we've got P max. So we've got random normals, and we want to basically threshold them at 0 and 1. So we want to set anything negative to 0 and anything bigger than 1 to 1. So you might, one reason you do this is for fitting a linear spline to data. And here we're getting, again, we're getting a not so bad. There's still a sort of factor of 2 difference. And these aren't worst case by any means. These are things where everything has the same type and so on. You can get bigger differences in more complicated settings. So they're worth mentioning because it wouldn't necessarily occur to you that this could even be a problem. Also on slow functions, LM and GLM and some other functions, for example, coxph and the survival package and so on, these are wrappers for underlying functions that do the fitting, lm.fit, for example, for linear models. And these are one of the nice things about R, that you don't need to worry about anything about the design matrix yourself. R will just build it for you. You give it a model formula, R will go off and build the design matrix, and you don't even have to think about it. But you do have to wait for it to get done. And it can be worth constructing the design matrix yourself if it's really big, or if you're doing a lot of them and they're simple. And you know enough linear algebra to use the functions. So, and the issue there, it's partly that you have to make a data frame that has all the relevant variables in it, and then you have to make a design matrix. So there's a bunch of steps, including a lot of memory allocations. And it's partly the slightly bizarre thing that one of the things that takes up the most time is coming up with the row names for the design matrix. So if you have a big design matrix, it's got row names, it's a matrix. The row names are just 1, 2, 3 up to however many. But that's still a character vector of a lot of entries. And bizarrely, this is one of the computational bottlenecks in doing linear models in R. Or at least was before R3.5. It's been killed in, is it 3.5 or is it the next RDevel that's been, it's in 3.5, yes. So R3.5 suddenly doesn't have this problem. But it's still going to, so the difference between these is smaller, but there's still a difference. If you have very large number of cases, then the big LM package will let you read your data in chunks and fit the model incrementally, chunk by chunk. So you can have arbitrarily large data sets and make one pass through the data set. Then another issue, which again there's being the alt-rep modifications to R have the potential to help with, is non-numeric values. So if you've got NA not a number or infinite values in numeric vectors, then they're typically handled specially in R because we want the result of operations on NAs to be NA. And also because the underlying numeric code that was written in Fortran 77 many years ago doesn't know from NAs. So here we've got an example, a matrix that's 1,000 by 10,000. So 10,000 rows, 1,000 variables. We're looking at the correlation matrix. And it takes about 6 seconds. If we just do this by scaling the variables to have zero mean and unit variance, and then just taking the cross product, then it takes about 1 second. Those would be equivalent if there was no missing data. And R can't assume that there's no missing data, because missing data is a thing, but you may know there isn't any in a particular setting. So even things that are basically matrix operations, there's quite a lot of effort goes into checking for missing data. That's again something that has the potential to improve in the future, because large objects will be able to have a flag saying we've looked and there isn't any missing data. But at the moment, you still get these sorts of differences. Yes. Okay. Yes, just a little bit before we start making you do things. Vectorization. So it's often worth using matrix and vector operations even when that involves doing more sort of basic computations than it would with a loop or whatever, just because the matrix and vector stuff is pretty efficient and the loops are pretty inefficient. So here's one of the sort of classic examples, convolution. You've got two sequences and you want to find the convolution of them, which is that thing. It turns up in a number of areas in probability and time series and so on. It is an actually interesting operation. Here's the basic R code that just translates this formula. You loop over the elements of x, you loop over the elements of y, and then you multiply those together, and then you add that to the appropriate element of z or z, depending which country you're in. And so this takes mn operations. And implemented in C, this is actually fast. You can partly vectorize it quite easily. You can get rid of one of the loops quite easily. That basically you can say will operate on all of x at once, but will operate on all of y at once and one element at a time of x. So here we're saying that we've got all of y and the jth element of x, and then this is the relevant elements of z. So that's certainly worth doing. You can also fully vectorize it, which is you do a sort of complicated trick that involves creating a matrix that's like, the only way to understand this is to actually write it out with numbers. It doesn't, but it lets you get a fully vectorized operation, convolution. Basically, you set things up so that the sums you're doing end up being row sums of a slightly expanded matrix. And the second version is certainly going to be faster than the first. Whether the third version is faster than the first is actually very sensitive to your machine and your version of R and stuff like that. So conv1, the slow one, takes about 20 seconds on this example. Conv2 takes about half a second, and conv3 takes a little bit longer. And again, those times, I've seen versions of R in the past where 3 was faster than 2. This is also one of the most realistic examples where the byte compiler does really well. After you run the byte compiler over this, it goes down from about 20 seconds for the straightforward version to about 2 seconds. So you can get, occasionally, this sort of improvement for free with the bytecode compiler. It doesn't happen very often, but it's nice when it does happen. So this is an example of vectorization working, and it's also an example of the bytecode compiler working. But the other problem with this version, this fully vectorized version, is that it makes an m by n matrix. And if m and n are large, then an m by n matrix will be large, and so you'll run out of memory for much smaller values of m and n with the third version. So if m and n were 1,000,000, then the second version would work perfectly well, and the third version would be a complete disaster because it would be trying to allocate more memory than you've got, far more memory than you've got. So that's the sort of trade-off with vectorization approaches, is that they typically use more memory. They often use more memory but to get faster speed, and that means that they work really well up to a certain point, and then the performance plummets, which means that you need to be careful about timing things not just at small sizes, but at the sizes of problem you actually care about. Okay, example. This is a simplified but otherwise realistic example of a power calculation. We want to design an experiment that will do where the calculation at the end, the analysis is a paired t-test, a one-sample t-test. And so we want to know what the power is, what proportion of these t-tests will return a p-value less than whatever our threshold for interesting p-values happens to be, like 0.05, for example. This is a very nice way of doing power calculations because it's completely general. If you know enough about your experiment, if you don't know enough about your experiment to write this code, then there are things you need to think about your experiment. But it can be quite slow. Anyway, so what should we do? How should we speed this up? So talk to your neighbor about this for a few minutes. The first thing we should do for this to speed up this code. Yes! Good, someone was listening. So that's a straightforward timing. What we really want to do is profile it. So we turn the profiler on, we run the code, which is actually a little bit short. We might want to run more copies of it. And then we can use summary rprof is one thing we can use. And so this tells us how much time is being spent in each function, both how much time is being spent in the function itself and how much time is being spent in the function and everything called from it. And we get the information twice. The first time it's sorted by this self time, and the second time it's sorted by total time. So if we look sorted by total time, well, it spends 100% of its time inside system.time because obviously it does. That was the outside and so on. If we look at self time, well, we're spending 20% of the time doing t-tests, which seems plausible. We're spending 10% of the time in stop if not, which doesn't seem like such a good idea. 10% in match.call, which again, why that doesn't seem like such a good idea. 10% in rnorm makes sense. 7.5% in mean. But there does seem to be quite a lot of somewhat surprising overhead going on here. So what we might try and do, so what might we try and do next? Yes, so the problem is that we've tried to find out which piece of code, this is the resolution of the profiler because it only goes as far as what the call stack is. It doesn't go as far as lines of code. So what we can do though is say, well, t.test.default is doing most of the work. We don't need all the output of that code. Well, first we can look at that. That used to work. Okay. This is, there's quite a lot of this, is the first thing you notice. given that a t-test is a relatively simple thing. And if you go and look at it, it's doing a lot of stuff. For example, checking that we've got the right number of enough observations, which, you know, we're designing this data. We can make sure we do. Various special cases, all sorts of other stuff. So it's sort of plausible that we can just strip out some of the work we actually want to do, and implement the t-test ourselves. That is, if you happen to know how to implement a t-test. And for a t-test, you probably do. If it's some other more complicated thing, then it's the question of whether it's worth finding out. So here we have, well, the t-statistic is the mean divided by the standard error of the mean. And then we've got have to look up the tail probabilities of the t function with the appropriate number of degrees of freedom. So if we compare that to the first one, so the first one was taking about 0.9 seconds. We've got it down to about 0.4 seconds. And this is a good point to Okay, so we aren't calling t.test.default anymore, and because this thing is taking about a bit less than half as long, all the percentages are sort of twice as big of the things. So we're now spending 20% of the time in stop if not. Quite a bit in garbage collection is.dataframe. And rnorm, well, rnorm doesn't seem particularly useful. Rnorm, can't be sped up particularly much, but the stop if not looks a bit strange. One thing that this doesn't show is spending a lot of time in PT, in looking up the tail distribution. Now, and this is an example of the sort of useful negative use of profiling, because you might otherwise look at the code and think, well, the t-quantile function is actually a really messy thing. You'd have to look it up in Abramovitz and Stegen if you were trying to implement it yourself. And, you know, maybe that's what's taking a lot of the computation. And so you might have tried to work around that. And we know that we don't have to do that. But, so you could have tried to work around it. Say, what's the critical value for the t statistic? Compute that once and get it out of the loop. So just looking at this code, you might think that this is going to be an improvement. We know it's not going to be an improvement because we profiled it. And let's just confirm that that's right. And it's not an improvement. It saves a couple of hundredths of a second. So that's an example of how profiling can stop you from optimizing things unnecessarily. So we're now at this point where overhead that we can't really track down very easily seems to be a big part of the timing. And so this suggests that it would be really nice if we could find some way of doing more computations at once. That the problem is that we're only working with tiny little vectors of length 100. There's a lot of overhead per cycle around the loop. So one thing we can do here, which, again, this is a trick that works until you start running out of memory, when it then spectacularly doesn't, is to try and do all the computations at once on a matrix rather than in a loop. So rather than doing well, it was previously 10,000. I've put it up to 100,000 because otherwise it would be too fast to measure. We're going to make a matrix that's got 100 rows, and we're going to have all 100,000 of those vectors in that one matrix. So it's got 100,000 columns and 100 rows. So that's the entire set of simulation replicates that we were previously doing in a loop, we're currently doing all at once. The mean, one of the basic parts of the t statistic, is the column means of that matrix. We also need the standard deviations, and there's probably a package that does efficient column standard deviations, but because there's probably a package that does anything. But in this case, we do reasonably well just by saying that the variance is the mean of the square minus the square of the mean, and then square root that. And so this gives us the t statistic, and we compare it to the critical t statistic. And so doing 10 times as many takes, so we've got about a threefold speed increase there. Doing 10 times as many takes about 3 times as long. You'd need to, you could, again, timing it, it's going to vary a bit. But we're getting, it's got a nice speed improvement there. And again, we might say, okay, square roots are difficult. Maybe we should strip out the square root. And that's something you might think of if you weren't profiling it. Let's profile it. And actually, the square root doesn't even appear in the profiling output. And that's for 2 reasons. Firstly, you only do 1 square root. And secondly, square roots are actually not all that hard. They feel hard because if you were trying to do them by hand, they're a pain. But they're done in hardware nowadays. The floating point coprocessors do them in hardware. And so they're not actually that much, they're not a big deal. And now we're getting to a situation where we're spending more than 80% of the time generating our random numbers. So unless we can speed that up, there's no point trying to optimize any further. So can we speed that up? So this is the example of something we know not to try. Well, so can we speed up generating the random numbers? The answer is yes, we can a bit. In this case, because we don't need particularly good ones. There's a whole bunch of options for how normal random numbers are generated in R. And the default is the slowest of the available options, because it's also the most accurate of the available options. Now I need to look up the syntax again. Normal.kind. And so we've got another sort of 30 or so % improvement by switching to another normal random number generator. However, you might wonder why this isn't the default. And the reason it isn't the default is that you can get simulations where you start getting the wrong answers with these other random numbers. So basically the problem is R generates 32-bit random integers and then has to turn them into normal distributions, and that means you only get 2 to the 32 possible values in your normal distribution rather than infinitely many, and they end up being a bit discrete in the tails, and also a little bit correlated in the tails between adjacent values. And mostly that doesn't matter, but if you're doing some simulation that's very sensitive to the tails, or the joint tails of consecutive numbers, then you won't get as good results if you use one of the other generators. And so this is us being relatively fanatical about accuracy when feasible over speed. But in this case, it's not going to be a problem, and so you can use the fasteR random number generator. So there we've gone from, initially we were doing 10,000 of these in about a second, and now we're doing 100,000 of them in about half a second. So that's a 20-fold speed improvement, which is worth spending a bit of effort on. Particularly as if this is a power calculation, you're going to be running this with a whole bunch of different parameters and different possible budgets and all that sort of thing. And so we can see both that sort of general principles help, but also that timing things to see what matters also helps. This wasn't a case where memory profiling would be useful. We weren't running, everything involved was pretty small. But if we'd wanted to do a very large number of simulations rather than 100,000, at some point we'd start running low on memory. And so if we'd been doing genome-wide association studies and wanted to look at the really, really extreme p-values, 10 to the minus exciting, as you do in genome-wide association studies, then you might need to do 1 billion simulations, and then this vectorized approach would start breaking down. And so there, memory profiling would be useful. Questions? Okay. Related, this is a very slightly simplified real optimization problem. We've got 10 genetic variants in a gene, so they're correlated. We want to do a regression of blood pressure on each of these one at a time and look at the largest Z statistic of the 10 and say what's the null distribution of the largest Z statistic of the 10. If they were independent, you could do this with maths and it wouldn't be too hard. But if they're correlated, you can't really do it with maths. You have to do it with simulation. So we're doing basically a permutation test at the gene level for an association between gene and blood pressure. If you don't know anything about genetics, SNPs are just variables that take the values 0, 1, 2. So we've got nice simple code. We've got a function 1SNP that takes a X vector, a permutation, and a data frame. So the name of an X vector, a permutation, and a data frame, and does the linear model and returns the Z statistic. One gene applies 1SNP to all of the SNPs in the gene and returns the largest absolute value of Z statistic. And one permutation, well, it takes a permutation of the observations and then does the one gene analysis to find the largest Z statistic. And if we want to do the permutation test, well, we want to do lots of permutations, so we might do 1,000 or 10,000 or 100,000 runs of 1.perm. So this gives you a nice simple way of writing the code. Then we've got the real, so this is the permutation distribution, this is the real value, and the p-value, permutation p-value says how many of the permutation values are below, what proportion of the permutation values are smaller versus bigger than the real one. So where is this going to be slow? again, what should we do to speed that? Again, talk to your neighbour, think about it a bit. Yes. Example bp.r. There's a bunch of example bp files. It's the first one. Yep. Yes. So all these, both the R Markdown file that these are literally made from and a bunch of R files of examples are on GitHub. And so you can get all the stuff there. You should have got an email from me some time ago with saying that it was going to be there, but at the time it wasn't. How did you call that file? Oh. Okay, so it's the example bp.r. Actually, it appears that we're due to have coffee in like 4 minutes. So I suggest that you go think about it over coffee and we'll come back and talk about it after coffee.